When the world gets tough and darkness takes its toll, there's a shining light, a secret I must unfold. Variational art encoders, they hold the key, unlocking infinite art and music. Let your thoughts run free. Coding brushes on the canvas, a tale never told. There is shining art encoders, they'll break the mold. With acoustic guitar and a beat from the drums, we'll create melodies that resonate. Our minds have just begun. Unleash your creativity, let your imagination soar. There is shining light encoders, opening every door. Art and music intertwine, a symphony in the air with acoustic guitar and drums. Our souls are laid bare.
Yeah, welcome to the MGM course, and we were doing Sinkhorn based generative modeling. So we quickly go through this. We already did this first part. So this idea is motivated by optimal transport. So basically, in optimal transport, we want to learn how to optimally distribute, optimally move one distribution to the other. So this could be applied in the case of images where we want to move the real distribution, where we want to move the parametric distribution to the real distribution. So that's the process of learning how to basically move. Okay, so this is another approach to get to generative modeling. So we have seen all these things in the last class, so we can just skip over this. I forgot to comment this. Yeah, so just to review, so OT with, so basically it's an OT with equality constraint. So this is what we are supposed to, I mean, not this, but yeah. So this is the OT problem we have. We want to compare two distributions P and Q, and we want to minimize the Wasserstein-1 norm over all the joint probability distributions whose marginals are P and Q. So in the discrete setting, this joint distribution is a matrix we have seen in the last class. So basically the row sum should be P, and the row or the sum across the column should be P, and sum across the row should be Q. So this incurs a equality constraint. Okay, so we can see this as an equality constraint problem. So this is OT with equality. So this is essentially an optimization problem with equality constraint, okay, in the discrete setting. So, but then this itself was not really tractable in the terms of algorithms optimality. Okay, so we this is a linear program. We can see this cost as a one big vector, and this pi is, we can also, is a matrix, but we can make it into a vector, and we can think about a dot product. So this is a linear program in the variable pi. Okay, this is an optimization problem in pi variable, and C is some vector, cost vector. So basically it's a linear program with equality constraints. So entropy-based regularization was applied, which amounts to this, which says that you add an entropy term, which is h pi here, and lambda is the regularization parameter. So depending on, so this is a hyperparameter as such. So depending on how much you want to regularize, you can add, increase or decrease this lambda. So overall, the first term was a traditional OT problem, but then we have these additional regularization term. So what we have seen in the last class is that itself will be strongly convex. Okay, so linear plus strongly convex will be strongly convex. So this connection where we could see the original OT with entropy regularization is equivalent to KL divergence. Okay, so then essentially our problem reduces to we can see another view that we can go with minimization of the KL divergence, which is same thing as solving the optimal transport with the regularization. So we had this few things set up before we went ahead with the algorithm. Basically this regularization term is strongly convex, which obviously means that linear plus strongly convex is strongly convex. So I have uniqueness guarantee, and then furthermore, if there is a compactness of the set where these joint distributions are with marginals P and Q, again we with the compactness argument and so on, we expect that such optimal map, transportation map will exist, and so basically all this, the extreme value theorem will kind of guarantee that, and convexity implying continuity will ensure all these things. Okay, so all this we did in the last class, existence, uniqueness, all this is there, and so basically this was the setup that we had in the last class. So we have this OT entropy, and we use some notation C and D for the sets of joint with marginals P, set of joints with marginal Q, and then eventually it's about finding an intersection of C and D. Okay, so that's what we try to do that, and then we described a projection algorithm. So it so happens that P, C and D are closed and convex sets. So that's very nice, because then we can think of projections which are unique, because when I project on a convex set, we do get unique projections. So that makes these projections interesting, and then the idea is that if you do alternating projections on a convex set via the projection mappings PC and PD, then essentially you should go to some intersection point of C and D. Okay, so we have not done this convergence proof that it does go to the intersection point, but we rely on the existing result that these projections do get to intersection if those sets do intersect at all. If they don't intersect, then it at least finds out the minimum distance between the two convex sets. So we have done that. So we do assume that they intersect. Okay, so we assume that there will exist a joint probability distribution with marginals P and Q. Okay, so that's what this set C and D mean. So we assume that because of the convexity argument, and we also refer to this original paper which does guarantee that. Okay, so when you do these projections on a closed convex set, then these projections. So this whole proof will be in this paper. We just use it as a tool here. So then essentially it's about projecting alternatively. So we did that. So since it's alternate, then we can think of odd and even projections. So basically the KL is kind of like measuring these distributions pi and pi lambda L. So obviously these sets are the one with marginals P and Q, and these are the ones which we are alternating. So you can start with one of the pi in any of these pi P and Q, and then you keep projecting. So we had this equality constraint, so we put that because it was not just the minimization of KL divergence, but then it was with the additional condition that if I'm minimizing with respect to the joint distributions with marginals in P, then I look at that equality constraint, and then I form the Lagrangian, and then I have these min-max formulations. And then we can change the min-max thanks to the strong duality, because there are no inequality constraints to check strong duality. I mean, strong duality is valid trivially, so we may put this mean on that side and then look at the mean problem. And then first order optimality equate to 0, and then from there we solve for the iterates, and all this we did in the last class. So then finally, yeah, what we get is this E form, but then eventually we have to get this pi iterations. So basically, this is the iterations we are looking for. The new pi depends on the old pi, like this. Okay. So this is a generic form, and since it's alternate, we want to see this as an odd and even. So we make one iteration as odd, another one as even, and then we finally have these two iterations, even iterations and odd iterations, and that's it. Okay. So at some stage it will converge, and then basically at some stage the scale divergence will not give you any improvement, because scale divergence is comparing between these two. So at some point, if they do intersect, they will become equal, and KL divergence will not change much. So that will be the time when you will stop. So only problem in this is that these are iterations running in matrices. So this is from complexity point of view, it's n square complexity being depending on what is. So you may, if it's a m by n, p is m and q is m dimensional, then it's m times n complexity. These matrices are like that, and this is quite costly because you're running this in terms of matrices. So there was one insight found that you don't really have to run these iterations in matrices. These iterations could be run in terms of vector iterations. Okay, so there is an idea where there is this insight that the joint distributions could be seen as some form of as this form basically. So joint distributions are can be written like this, where this is a diagonal diag of u, where u is a vector, n dimensional vector, and v is a m dimensional vector. So this is called matrix scaling. So the idea here now is that rather than running your, if this is true, then the idea here is that running your iterations in pi, can you translate this to running some iterations in the vectors u and v iteratively, because u and v are n dimensional. So at each iteration you will be your complexity will be n, and updating the v complexity will be m. Okay, so that was the insight, and there is a proof for that which I can quickly go through without kind of like. So this was the original Lagrangian, and this is the one we have, and the first order optimality conditions will give me this. So there will be somewhere lambda here. I guess there will be one lambda term here. So we can. So there will be a lambda term here. So this is fine. Okay, this is the Lagrangian if you consider the joint, right? So this was the equality constraint, and this is these were two where this is the Lagrange parameter for the equality constraint that says that the pi column sum should be p, and this is the Lagrange multiplier where it says the row sum of the pi should be 1. So we incorporated this, and this was our original OT with OT entropy term. So basically we have this Lagrangian, and we did this. So we were looking for the optimality, and then we so in the optimal case, partial derivative of this with respect to pi should vanish. So eventually what should I have is this. You may verify this calculations, and then simplifying, so solving for the log will give me this quantity. So basically lambda was moved to the denominator, and solving for pi now. So then log, if I have to send it on the right hand side, then it will become exponential. So this guy will become exponential, and then the c lambda 1 will be exponential. So that c lambda c divided by lambda is put in the center, and this g y by lambda and f x by lambda is kept on the side. And as you can see now, this is kind of, you are looking into this form. So at the center what you have was indeed k. I mean, you have to recall this in the last class how k was defined, but you can trust me that k was indeed is e to the minus c xy by lambda. So this was our k, and what we have with these reformulations is that we have these guys on the side. What is on the side, that is like these diag of u and diag of v. That's how we see this. So from this derivation or the insight, what we found out is that the joint distribution is seen as this form, okay, which is eventually this form. So I can say u is a vector like this, because this is a vector because it only depends on x. But then the way it is going to multiply with the k terms, I have to make this as a matrix. Okay, so this is a vector, but the way it's going to multiply with the k, because yeah, so it will be like pointwise multiply. So that's why I have to make it into a matrix again. So although so this u will be like this, right? And this k is like this, and v will be also diag of v. Okay. Although this diagonal is just this guy, fx by lambda minus half. So this is like just however many x you have. So basically this is a vector, but the way it is getting multiplied is that this guy is getting multiplied with this this row. Okay? This guy is getting multiplied with this row. So that's why we have to make it a diag. Okay, to make it equivalent to this guy. So we did this. So basically u is this guy, and v is e to the gy by lambda minus half. So this is our v. But again, since this is multiplying kind of like the column wise, so we again make this a diag. So there is this thing done here, some adjustment done here. I hope you can check these things. So basically what we have now is this insight that the joint distribution is of this form. So this form is interesting eventually. Whether you understand all doesn't matter, but what you have is this. So, and the iterations that you were doing in pi, right? Remember the odd even iteration that you were doing. Can you now, with this insight, can you change this to iterations that involve only vectors? Okay. Diag as such doesn't create, because this is theoretical thing that I will multiply the diag, right? It would make it a matrix, and then I will multiply. But even if I make it a matrix, it's certainly not the case that I will make it a dense matrix. I will keep in mind during implementation that this is a vector as such. So as such, this won't be a matrix complexity when I'm actually forming these. Okay. So I will adapt my code in a way that it remains a vector-wise operations. But from the actual view, it should be of this form, diag of u. Okay, you are just supposed to kind of ignore these off-diagonal 0 entries, because otherwise if you create a dense matrix diag of this, obviously you will again spend up doing m by m, because u is kind of m, I guess, because x dimension is, u is n by n. So if you indeed create a dense matrix and then multiply again, it doesn't help. So in the discrete case, matrix scaling problem is about finding u and v that scales rows and column of k. Okay, so then if we have to formulate this in a slightly different way, then our marginal is p, and which is indeed sum across the columns. So this is seen like this, and then if it is q, then we have the row. So we multiply, we sum across the rows. So that will be equivalent to 1 transpose pi. Okay, so basically doing the sum across the rows. So as a start, you can start with u and v defined like this as an initial guess, and then your iterations will be now ul plus 1 will be p divided by, this is a pointwise divide basically. Okay, so this p divided by kvl. Okay, so and then v will be we can be defined like this. So why this will matter? Actually, there is another proof which says that if we go with this iterations, so it may not be evident right now, but if we go with this iteration, we indeed get back to those iterations that we have for pi 2l and pi 2l minus 1. So there is a proof where we can say that now instead of these matrix iterations that you were doing, now if you can do this type of iterations, then this is equivalent to doing these odd even iterations for the matrix we had. So there is a formal proof for that. Intuitively, it may not be directly clear. So this is exactly what we are supposed to do. Okay, and if we look into this, then obviously now, and this is a this, if you see, this is a pointwise divide. Okay, because P is a vector and KVL is also a vector. So obviously you cannot divide vector with a vector. So it is a pointwise division. Okay, so pointwise division in this sense that if it is xy, then it is the vector that I get is x1 y1 x2 y2 dot 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 xn yn. So this is what we mean by pointwise divide. Each entry of x corresponding entry of y gets divided. Okay, so with this notation being clear, this is exactly the iteration you are going to do, and that's it. So that's also another way to have an equivalent form of the primary trace that we had before. So so this is the claim that with these choices of the trace un and ul and vl, which are defined like this, we obtain the primary trace which we derived in the last class was with pi 2l and pi 2l plus 1. So there is actual proof. I guess I have that proof maybe. Yeah, it seems like I have that proof. So let us see that why is that the case. Okay, so this is the argument, right? So this is the claim: running iterations with vector ul vl is much cheaper than running with the primary traits with matrices pi 2l and pi 2l minus 1. Okay, so to see this, we run the primary traits with the choices of ul and vl and use the notations this. So we run the iterates with the primary traits that we had before, and there because we know that pi was defined to be like this. So pi is defined in the terms of diag of u k diag of v. So what we are saying is that, okay, if we are proposing this u and v, then what if we substitute those u and v here? Do I get the same update equations that I had for pi originally that I had, right? So basically, can I get this with these choices of u and v? Can I get this exact form of the even and odd iterates? So that's what we are claiming, right? So to run this, we run these original this with the choices of ul and vl. And since we are running with choices of ul and vl, we adopt this notation that instead of saying pi, because we want to verify that it is actual pi, so that's why we say let us start with this notation tilde. Okay, so pi tilde 2l. Let us see whether pi tilde 2l eventually comes out to be the pi 2l, right? So that we originally derived. So we use that notation, and now we are saying that let us pick those choices of u and v that was suggested, and let us see if we get the original form of the pi tilde. So pi tilde 2l, we can write this as diag of ul plus 1 k diag of vl. Okay, so we have the recent updated u with l plus 1, and we have the old one, and then at the next step we know that 2l plus 1, now this will be frozen and this new vl will be taken. Okay, so that's how we go about that. So what we are saying is that u and v alternating is similar to like having even update of the pi tilde and odd update of the pi tilde. So let us change l to l minus 1 in the second one. Okay, let us see if this is claim is okay. So if I change l to l minus 1, then I get pi tilde. Sorry, this is on the top. It's a superscript. So pi tilde. So l to l minus 1 here. So this will be 2l minus 1, right? So this is 2l minus 1. This is diag of l to l minus 1. This will be ul, and this is like k, and diag of l to l minus 1 here will be vl. So it seems to be okay. So from there I will say that k diag of vl could be pi tilde 2l minus 1 divided by the diag of ul. Okay, so we derive this guy. It's just that you change l to l minus 1 here, and whenever so you when you divide, it's pointwise divide. Okay, so in other words, what you can say what you can say that you can also go back here from here. Okay, so this is a valid derivation, you can say. Okay, so here the division is done in a sense that it's pointwise. Okay. Okay, so now substituting the value of k dig VL from 15 in 13. So from 15 in 13. Okay, so k dig VL is what is going to be substituted by this guy. Okay. So if that is the case, then we look at pi tilde 2L. So this is dig of, this remains the same obviously, and in place of k dig VL, we put this guy. So this is pi 2L minus 1 dig of UL. So that's correct. So then, so this guy remains the same now. Pi tilde 2L minus 1 divided by dig of UL. So that remains the same. So it seems like as if we have substituted the UL plus 1. Okay. So UL plus 1, the way it was defined, the UL plus 1, it was defined to be P divided by KVL. So if I'm taking a dig of UL plus 1, then I will also take a dig of P divided by KVL. So that's what we are doing here. So dig of UL plus 1 is now dig of P divided by KVL. So all this is fine, and then we have, okay, so there is some dig done here, and pi tilde has been, okay. So there is this dig here, and there is this dig here, right? So this dig has been taken common, okay? So this dig and this dig are combined now, because there is a diagonal matrix, and then we are dividing by another diagonal matrix. So we can take it, so this is like same as this. Okay, so it is like easy to verify that. Okay, so dig of P divided by KVL and then divided by dig of UL can be rearranged in this way. Okay, so that seems to be okay. Okay, basically P divided by KVL pointwise, but then each entry you also have this combined. Okay, so this is kind of okay. It's a diagonal matrix, so these things simplify quite a lot. And then we have this remaining part pi tilde 2L minus 1, and that's it. So I guess dig of UL KVL. Okay, so dig of UL KVL. So basically here again I do the L to L minus 1 change. Then I have pi tilde 2L minus 1 in the same way we had previously, right? And this is equal to dig of UL K dig of VL. So that's fine. Okay, from here we change L to L minus 1 and we get this. And so what we had is this guy, but if you see here, then if you see this guy, right, so there is a slight change that this guy has a dig involved, whereas this guy does not have dig involved with VL. Okay, so there is this, so but this will be equivalent if we multiply by 1m on the both sides. So basically that will be that will make this dig of VL at VL. So if you multiply one vector of all ones, right, this is vector of all ones. So basically we have to multiply vector of all ones here, because then, okay, if you see this guy, right, this is VL, and what we have here is dig of VL. So to change dig of VL to VL, we got to multiply by 1. Okay, so dig of VL times vector of all 1. Now it will make it a vector VL, which is what we wanted. So here this guy was vector VL, and from our derivation it was dig of VL. So to make this guy VL, we had to multiply by 1, but this means that on the left hand side also I have to multiply by 1. So that is why you see this guy is now written in this form, that it is pi tilde 2L minus 1 times 1m. Okay, so that's taken care of. So all this is fine, and this guy remains the same as before, we just copied there. So this derivation is fine. I hope you are okay with this. So what are we trying to do? We are trying to what is our original goal? Our original goal is to say that this type of updates is same equivalent to this type of updates. So these updates are happening in vectors u and v, which is like complexity m and n, and these updates are happening with complexity m times n, because pi is a matrix. dimension m by n. So what we have done is that we started with the pi, and what we said is like pi, we know that pi is of this form due to this matrix scaling theorem. Then what we said is that, okay, then use the iterates suggested for u and v and make sure that pi tilde updates are the one like we had before. Okay, so then this is what we have. Pi tilde 2l is of this form, diag of so okay, so we substituted that and we have pi tilde 2l, then diag of okay, we start like here, right? So that's where the similarly picks up. Okay, so this was the first derivation starting from, this was the starting point where we said k diag of vl is this, and then similarly we say diag of uk is this. Okay, so here it's k diag vl and there it's diag uk. Okay, so we start in the same way, and then we do those similar kind of manipulations and all those. There was a point where we have to kind of use the way we do the updates for UL. Okay, that's a point we have to be careful about. So so these are the things we know, that pi tilde 2l plus 1 is indeed of this form, and then yeah, so the way we define these iterates, right, that ul plus 1 and how it gets these iterates are done with the scaling of k, and that gives us this this thing, right? So it's similar to what we were doing here. Okay, so I don't think I have to repeat this, even if it looks strange, but as I said, these are similar steps but with V, so you have to kind of do this. Okay, I'm not supposed to kind of like repeat this again. So so we verify that, okay, offline, that indeed in the other case we get this. Okay, so in the interest of time we can kind of assume that this is okay. So so what do we get, right? So what we get is that indeed these are the primal iterates. So pi tilde 2l plus 1, we could write it like this, and the even iterates pi tilde 2l we could write like this, and these were indeed the primal iterates. Okay, that's what we prove. By using the way u and v are getting updated, we arrive at this even and odd iterates that we proved in the last class. So which is what we have here. So we got this even iterates, which was equivalent to the primal that we derived before, and this odd iterate is also matching with the original derivation that we had. The way we change u and v will indeed lead us to the same solutions that we had before. So outcome of this is that you should run iterations in u and v, which are vector wise iterations. Now when it comes to generative modeling, then all this could be made into a nice scheme. So so what happens is that we have a generative model block here, which is in this form, so which is actually blue, but I cannot see it here. So as usual, the random vector goes in, and generative model is trying to produce something interesting, which in this case it's x1 to xm. So so it produces some image, let's say, and this image and this is the real data. So this is let us say the corresponding cat image or something like that. Okay, there will be some random vector which will produce some image, and there is a real data that is going in, and that real data, there are maybe let's say n of them, and there are these and then you have a cost corresponding to these data. Okay, so then this cost matrix is computed, and once the cost matrix is computed, then you can use that. You remember the way the k was defined. It is exponential of minus c divided by e. So obviously k is a matrix because c is a matrix. So this is like pointwise exponential of the matrix c by e epsilon. Okay. So this is what happens. What you generate, what the real data goes in, cost matrix is computed, and then it goes into the Sinkhorn algorithm where the iterates for V and U are done, as we have shown previously in the theoretical stuff. So this is the Sinkhorn algorithm part, where you are kind of estimating the x distribution, the one. So you are kind of estimating the, or let us write it this way. So this is your p theta distribution, and this is your p real distribution. So Wasserstein distance is kind of being computed for these guys. Okay, so basically you are computing the distance between these two distributions. Okay, and this p theta distribution is generating this via the generator, which has these parameters theta 1 and theta 2. So this is being generated, and then it is being compared with the p, and we know that so since we are using this one num Wasserstein, so it's an optimal transport problem. So basically there is this cost involved, and then we construct the matrix K that we have seen, and then it's about finding the cost estimate, the current cost estimate. Obviously these thetas are not yet optimized, so initial cost will be very high, because this Sinkhorn algorithm is calculating this distance only, that's all. There is no parameter anywhere here or here. Okay, so you are producing some data from the generative model, and it's just now because this p will be calculated from the input distribution there, and this matrix values are kind of the cost comparisons that we are doing, right? So this is what we have, and we have this K computed, because this was somehow related to so we go to the K Lagrangians, and we created this Gibbs distribution, and somehow it's related to the OT. So this part we have already done that, so intuition of this can be found from there. And once we have this, essentially we just have to run Sinkhorn, the matrix scaling type algorithm, to update UL and VL. And once you have that, I think there is a mistake here. So this will be U, and this will be V. Okay, so I took this figure from the original paper. I changed quite a bit from the figure, because the notations I'm using are UL and VL, and the paper uses AA and AL and AL and BL. So I forgot to change only this part, I guess, but everywhere it's okay. So the final, because this is the iteration, right, and this you will run up to the Lth step. So since you will run up to the Lth step, the final step you will produce UL, U capital L, and V capital L. So once you have that UL and VL, you put this in the cost. So this is the loss function that we have. So UL so this is the inner product, right? So this is like UL transpose C pointwise K. So this was the cost, or the original K that you can think of, right? And this is like VL. So this is the checking the measure, right, of these two distributions. So eventually, you know, how the generated distributions, how it is far from the real distribution, is all now dependent on this cost, because this is the final. Everything boils down to this computing this inner product eventually. Okay, so they are like related, and that's what, because Sinkhorn doesn't give you one short way to compute this. Okay, so you did this iterative method, and then you are here, and so this is estimating. Of course, how long you do this L and something, that also depends. What is your good estimate of these distance of the two distribution? But let us say you did L iterations, and basically you will do this L iterations, because eventually there is this there will be a point where you will stop, because the K Lagrangians will say, okay, that's it. So but the problem is, in the first step you won't be able to get the best cost, because the distributions that you are producing from the generative model, which is in our case is p theta, and the real distribution p, obviously they will be very far from each other. Okay, and this will be reflected in this cost in this cost calculation, that this what we are trying to kind of compare these two distributions, and then we know that okay, they are quite far from each other. So in that sense, this is the loss we have, and then we do this this gradient back propagation, right? So but this back propagation will not affect any of these blocks. So these blocks remain independent of the back propagation. So basically, only thing that back propagation will do is go back to the generator block, which is this block. So this is where the parameters of the network will get updated, theta 1 and theta 2. So generator will become more powerful, and then it will produce another set of samples, and then another set of real distribution goes in. They will be compared again, and if the distance is again too high, then the generator will be asked to update the weights again. So that way, it is it is quite different from the generative models that we have seen. And there are some open-ended research also that could be done. And this is not considered to be state-of-the-art. Generative model, Sinkhorn-based generative model achieve I think 4.8 inception score, but what we have already seen is GANs can achieve close to 8 also already. Okay. So there is this still an open thing that although this looks very beautiful idea, maths very nice, optimal transport is a deep theory involved there, and yet so as a researcher you might think what could be done to improve these type of model, because you do have a good scalable model now. Because earlier when we were deriving Wasserstein GAN, then we said that as such it's a very hard problem that we optimize this over all possible joint distributions. Then there was this later development where we said that there is this tractable way to kind of compute the measure of generated distribution and the real distribution. So there is this Sinkhorn algorithm that could be used, but then somehow the quality is still not up to the mark. So some of the open problems are, is it that the generative model could be made more powerful, because this paper was published 2015. I think not even before that, 2013, I guess. So as a research problem, because there are many interesting architectures that have come by now, so can we feed in some very powerful architectures in these models? We don't think Sinkhorn algorithm there is much to do there, because that's already proven its optimal algorithm. We already know that. So most of the research, it seems like it could be done here. I mean, this is hypothetical. We don't know, things somewhere other things might be going wrong. So can we improve this inception score from 5 to the current standard? Is diffusion models are even going up to 9, which we will discuss in the next class, I guess. So can we do something as a research problem? Okay. So there were results on style transfer and something. Somehow I could not put that figure here. So initial result on style transfer were promising, but as a pure generative model, it seems to be lagging. So I guess this was the Sinkhorn-based generative model. As such, implementation is quite easy. As you can see, it's a very simple thing. In fact, you just have one architecture, which is generative model, and then you plug in the Sinkhorn based algorithm, which should be there in the PyTorch. So it's as such, it's a pretty simple algorithm to implement. Okay, so that's, as I said, there is a generative model, input data, Sinkhorn algorithm. In the generative model, the random vector goes in and vector x is produced. And then this x is then compared to the input vector that corresponds to the real distribution. Calculate the cost matrix, then the k matrix, then apply the matrix scaling algorithm for L steps, and then compute the loss functions. And then you do the back propagation. So only tunable with theta in the generator, and you do the back propagation, and weights are updated. Okay. So again, this is a purely probabilistic model. So in fact, it is classified more as an explicit probability model, because here you actually get the distribution in hand. GANs never tell you the actual distribution. It's implicitly learning the distribution, but you never get back the you cannot go at any stage. You cannot look at the GAN data and say this is how I'm going to form the distribution. Generator is learning some distribution explicitly, but what is learning, it does not tell you. Okay, VA is more explicit approach. So we will try to see that. We explicitly get a hand on the distribution as well, and in that distribution we add some noise, and then we create the variations in the data. So we will recall a few things about VAE. Again, I'm not sure I will be able to complete the VAE today itself, but in fact I might have to skip the part, some part, I think. Okay, so we recall a few things. So first thing is divergence measure that we have already seen. So basically we will go back to the KL divergence. So this is the divergence measure. Sometimes you see change of notation here. So this is like D. Earlier we were writing like this, dp comma q. So this is the same. So this is the divergence that's defined, and then and any divergence, if it's 0, then the argument must be equal. So these are the definitions of the divergence, and divergence measures are usually weaker than the distance. We know that because KL divergence doesn't satisfy the symmetry or the triangle inequality, so it doesn't it does not satisfy the property of a metric or a distance. So all this is we already know by now. We have learned many divergence by now. By many I mean, okay, we knew F divergence, we knew KL divergence, and we knew Wasserstein. In fact, Wasserstein is even a distance. So these are the things we know. There are a few others like total variation and all. Those were quite popular in classical vision and so on. But I don't see total variation measures quite often these days. So if I have a CDF in the continuous case, obviously we take a derivative of the CDF to get the PDF. So these are the basic stuff. Okay, so before we start VAE, it's a good idea to know a little bit about probabilistic graphical models. And probabilistic graphical models were developed quite some time ago, where most of the things were seen as a probability model. So basically, any problem you want to study, you can consider a graph. You can look at the dependency graph of any problem, and then you can say which depends on what. So if you can recall in the previous intuitions that I gave, now those intuitions will take the center stage. Like initially, if you see in the beginning of the course, we were saying like this about pixels, and we were trying to generate. So let us say cat distribution is like this. Then I was saying that, okay, this is, so if I see a nose, then yeah, the probability of the distribution of the eye could be somewhere nearby and so on. So these are like very complicated, right? So basically what we said is like a bunch of pixels appearing define the next set of pixels that are going to be generated. Okay, so this is this is a not very easy problem, right, as such. So as such, we have said in the beginning that we cannot assume the complete independence of these pixels, obviously. Okay, so then these things were known, right, in many image processing problem or whatever problem you think of. So there are these pixels, right? So let me say that there are very few pixels. Now you may think about the dependency graph, right? So is there dependency like this, like this, like this? So basically you think in terms of graph, right? Whatever problem you have in mind, right? You can think of, you can make probability dependency graphs that this guy is responsible for this guy is responsible for this, and this guy, okay, this guy is responsible for this guy. So this is called A. But we can even say it's a DAG. So we can say that things start from somewhere and it flows towards some way. Okay, so we can say it's like a kind of a directed acyclic graph. Okay, so there is this concept of directed acyclic graph. So obviously there should not be a cycle, and then there are directions like this. Okay, so we call this a DAG because these edges are like, you can see these edges are directed. Okay, so we can build a dependency graph that certain data, certain type of data is dependent on some data and so on. So there is this modeling which which people used to do quite a lot. So there is a big, there are books on this probabilistic graphical models, because in those days these were considered to be the main way to capture the dependency, or even to formulate a problem. So the first thing you do is like, what is the dependency graph? Okay. And then you can write the joint distributions and try to estimate the joint distribution. Sometimes you assume some latent variables and then you integrate out the latent variable. Okay. So these things will come, but this was considered to be the modeling thing initially. Okay. So so we examine the distribution, joint distribution obviously, of x1 to xd within a directed acyclic graph. The DAG has nodes x1 to xd and directed edges between these nodes. Then the joint distribution of the DAG is given by this. Okay. So we are trying to understand the joint distribution. So it could be, let's say, pixels in a cat image, and then we can use the chain rule that we have seen even in the beginning of the class, that we can apply the chain rule. So this is a compact notation where PA means the parent of PA stands for parent. Okay, so PA denotes the set of parents for the node xi within this graph. So in general, it's like this is the formula we have. Obviously, if it's it depends on like the dependency is very dense or very sparse. So these calculations will depend, right? How much complexity this will have. So all is part of the all depends, right? How things are related. So in a DAG, there are always one or more root nodes that lack the parent nodes. So that's what we are saying, that there will be at least one or two root nodes that does not have any parent nodes. So there will be some xi for which the parent is null. For these nodes, the conditional probability reduces to the marginal probability p of xi, obviously, because there is no dependence before that. So then so basically here, because pair p of xi given PA of xi, and if xi was a root, then obviously this is phi, right? So this conditional, because phi is like nothing, right? So then this is equal to just pxi. That's what it's saying, right? So conversely, if we have a joint distribution, then we can infer a corresponding DAG by adding directed edges from each node parent of xi to xi. So if someone gives me this, then I can create the DAG, okay, because I just have to add the directed edges. Because I know the parent and I know xi from here, then it is very easy for me, because if I know the parent, then there will be an edge from the parent to the child xi. So that's fine. Now let us look at the quiz of the formula that we had, right? So let us see this very simple diagram of a DAG, I mean, where so this is the DAG, okay? So it has two nodes, Z and X. Now this is the formula we have. So write down the joint probability distribution. So in this case, your x1, you can say it's x, and x2 you can say it's Z. Okay. So now what you are supposed to find is this p x z from this formula. Okay. So what this formula says is the number of nodes is the d. So d is the number of nodes in the graph we have. So in the graph we have the number of nodes we have are the nodes we have are x and z, and there are two nodes. So this product will go from 1 to d. So let us start with the 1. So p of let's say x1 is our, so let us say this is our x1, this is our x2. So p of x1 given parent of x1. So parent of x1, which in our case is x, is z. And then I go to I equals to 2. So I equals to 2. So this is the product. I equals to 2 will be x2 and given parent of so in our case once again, so yeah, I will fill the x2 later on, okay, because we know what is x2, right? So p of x2 and then parent of x2, but parent of x2 is what? Null, because x2 is z, right? So z does not have any parent, so this is like phi. So let us put this, x1 was x, right? And x2 was z, and we have seen previously that that for a root it just boils down to itself, so which is x2. Again I should put a z here, so x2 is z. So in this case, if the problem is given like this, where something, obviously this is a very simple case, but the idea is that if you learn this for more complicated thing, then you have a way to write down the chain rule basically. Okay, so in this case, this is the joint distribution we have. Okay, and it turns out this very simple case is what is needed in the VAE. VAE and GANs both use this framework. Okay, in GAN and VAE there is a latent variable z. Okay, that's it, and that latent variable z is supposed to produce x. Okay, so that's what GAN does, right? So there is some g theta z generator that takes a z, given a z, okay, it produces x. Given another random vector z, it produces some another x. So that's the PGF PGM of GAN, and we will also see VAE. VAE is also similar. So already this very basic model is used for GAN and so on. So let us try another quiz with this slightly more complicated one. So obviously we are looking for, all the time we are looking for the joint. Okay, so x, y, z. Now we can say this is x1, this is x2, this is x3. It doesn't matter about the ordering. Okay, I could have taken any of these as x1, x2, x3, because in the end they will product and they will commute. So it doesn't matter the way ordering is done. It doesn't matter. So x1, I just have to make sure that x1 and their parents of x1, right? So this is like this formula, right? So P of x1, x2, x3 is, let us start with 1. So in our thing 1, 2, 3. So P of x1 and parents of x1. Okay, so P of x1 and parents of x1, there seems to be like two parents. So this is like z and y. Yeah, z and y times parent of x2 and parent of x2. So x2 parent is z, times P of x3, and x3 have no parents. Okay, so this is phi. So if we were to simplify, then this is x1 was, sorry again, so x1 was x given zy, and P of x2 was y given z, and P of x3 was z. Okay, so if there is a problem, we have to model and if it is like this, where z influences y, z influences x, and y influences x, then this could be used. Okay, so this is some sense of problem solving technique, right? You find out these dependencies, and obviously it may happen that you will approximate this further, because this may not be easy to find in general. So you may use some tricks, and in fact this is what we will do quite a lot in the following classes, to find a good approximations and so on. But if you see this model also, we have seen, so this could be used for conditional GAN. Okay, so it is z is given, but along with the z some label y is also given, and based on z and y I will be creating an x. Okay, so this could be seen as a model for conditional GAN. We have not seen conditional VAE, which we will see, but conditional GAN was this exactly like this, or because if you have a generator, you have a z, and then we have this conditional label that goes in, which is our y, and then it produces some x, then it goes to the discriminator. Discriminator takes some real x. And from this diagram, if you see, z influences y, right? But is it true that z influences y? I'm not completely sure, to be frank, because regardless of what z comes, my label y is what I choose. Z influences Y, is it? Z influences X. I agree, because Z will also decide what type of X will be produced. Because I guess this makes sense. This makes sense to me. Z and Y together influences the generation of X. Okay. Anyway, so this is one case, and then so you may do some more practice like this, right? If it's so we can do it very quickly now. Now we are expert, right? So P of x1, given parents of x1 is z1, z2. P of x2, parent of x2 is z2. P of z2, parent of z2 is z1. P of z1. Okay, so that's it. So that's the joint PDF of this model. Okay, so a few things we recall is Jensen's inequality. I'm not sure if I said this. So Jensen's inequality says that average of the function is greater than or equal to function of the average. But this is same. This is actually nothing but extension of convexity to the probability case. Okay, so what we remember is convex functions are like this, and what we say is the average of the function values fx, fy. So which in our case we call this as theta of fx plus 1 minus theta of fy, and then we say this is average of the function value is greater than or equal to function of the average value, right? So this is what happens for convex functions. This is what is the criteria. So this is being extended here in the case where you are dealing with random variables. So fx will be some random variable again. So this is exactly what is being said here. Okay, without going into the proof of this. So you just remember it like this, right? Expectation. So expectation is like the average, right? So you can say that average of the function is greater than or equal to function of the average. So with this we have Jensen's inequality, and obviously we are going to use it in the derivations later on. And we also recall lotus from the probability class in the first two classes that we had. And lotus is very simple. It is a way to compute expectation of a function of a random variable. So expectation of a random variable as such is given like this, but we are saying what if x was modified to gx? So how do you compute expectation of g of x? Okay, where g is some function. So the idea was like, okay, we can compute it like this. Okay, so the y that you get now, it could be written as just expectation of the PDF with respect to the original x, and then the function values that you have here. So that's it. So that's the way you are going to compute the to do the expectation. So if it was a discrete case, then in the discrete case the expectation of x is given by sum of xi p of xi. Okay, I equal 1 to m, let us say. So this is the expectation that we compute but what if someone gives me g of x? So what this lotus says is that it's very simple. You do g of xi and take the PDF of xi only. Okay, so I equal 1 to m. That's it. So this is what is lotus. So in compact form this is written like this. Okay, so we recall Jensen's inequality, we recall the lotus argument. Yeah, and we can have generalized Jensen's inequality. So if you compare the usual Jensen's inequality and the generalized one, you can see that there is this wherever there was x, now we can have gx. Okay, so we are not going to prove these results, but we just keep this in mind. This is more into prob and stats. So again the same thing holds. If f was convex, that is guaranteed. There is no restriction on g. G could be any, but f is still convex, and g is maps inputs to some scalar outputs in R. So it's a scalar valued. So that's it. As long as g is scalar valued and f is convex, then generalized Jensen's inequality holds. Okay, and then we already are familiar with the KL divergence. This is the definition of the KL divergence, and we have also proved before, in fact, that KL divergence is greater than equal to 0, and this follows from the Jensen's inequality that we have. So there is nothing more to do, and KL divergence is equal to 0 if and only if P is equal to Q. Now MLE and KL estimates also we have seen before. So if we have a data set x1 to xn approximated by the distribution p data, our goal is to fit this data set to p theta x. So one possibility we have seen was the maximum likelihood estimates that we are doing, and we have shown this that this is indeed equivalent to KL divergence minimization of the KL divergence, right? So I guess there is no doubt here. Okay, I think we have done this before. So now we have recalled a few things that we might be using again and again until next 4 or 5 classes. So as I said, VAE is just the first case. You remember that diagram? There is a latent variable z, and that is used to produce x. So as such, there is no, nothing to gain from here. But what we have is that the joint for this was pxz was p of x given z, p of z. So this was the joint distribution for this modeling, and so then what we are trying to say now is, so we have a generative model which given a z, it knows how to produce x. So we can put a theta here. So there is a generator, right? So given a noise vector, it is supposed to produce an x. So obviously that generative model is parameterized by theta, some neural network, and this is also our p theta, because this is now also dependent on theta. But the thing is, we are only interested in the x, right? So since we are only interested in x, what we want is that let us marginalize out the z, because out of the joint distribution, what I care about is the distribution that produces the x. So this is called marginalization, right? So I make use of some latent, intermediate latent. This is the recurring theme that you will see again and again. You will use some latent, but then later you will want to marginalize that. In this case, z is your latent. Z is latent because if it's a random vector, it's produced, but then you don't have a hold on what exactly is going to produce each time, right? So whatever Z is, we have a push forward which is p theta, which is the generator, and it's supposed to produce something. So that's why you see again and again you will see these things coming where we get this p theta and we'll say now let us marginalize. So that's why you see we are integrating with Z only. Okay, we want to get rid of Z. Okay, and so basically you integrate out the Z. Okay, so latent variable models are graphical models that we have illustrated in the figure 1a that we drew before, which was or the previously I drawn. So this is the latent variable graphical models in the context of deep generative modeling. Particularly for continuous data, LVM typically takes the following form. So if we for the moment think of a continuous modeling, then obviously we know the favorite one is the normal distribution. So if you recall in the GAN context also this was the case. So PZ that we were producing the random noise, that was via standard normal. So this is the standard normal. It could be multivariable, so 0 could be a vector of means 0, and I could be the vector, in this case is 1. So this is the standard normal, and what we do is generate the data given this Z via generative model, and we may ask for also for that to be also normal. Okay. That could be like my choice. Okay, that what if I also ask for that given a Z noise vector, and what I'm of course this may be a complicated one because this is multidimensional. Okay, so this g theta Z could be vector of many means, and then so it could be a high dimensional normal. Okay, so and then we have this sigma square I and so on. So so we may think of this form. okay, where Z is normal and the generated parametric distribution is, we are also trying to fit a normal distribution in there, okay. Although it is not very clear that the GANs are actually doing that, okay. So we don't know that the generator is, we don't know whether the generator is learning a normal distribution, okay, because GANs never tell us explicit distribution anyway. So, but in the VAE case, we will see that. Okay? So in the VAE case, we will explicitly try to make it like that, and in the diffusion models also, it is like that. We keep track of the distributions being generated, and eventually we make it a pure Gaussian noise in the forward and the process and so on. So for GAN, not sure, but we will see that we do get a hand on these. Where G theta is a neural network parameterized by weights, and then P theta x z for discrete variables defined by neural network generator. Okay. So the maximum likelihood objective is used to fit P theta to the data distributions, which entails the following optimization problem. So if we do a maximum likelihood estimate, then this is what we get. However, calculating the integral from the MLE objective is directly infeasible, because it requires evaluating the nonlinear transformation G theta z for each configuration of the latent variable z. So we may also look into the log likelihood. So earlier we had P theta x and P theta this, but then we can also look into the log of that. Okay. So we are looking at the log likelihood form, which in this case it's this. By leveraging the property of Jensen's inequality, so we can derive the lower bound of this log likelihood.
When the world gets dark, darkness takes its toll, there's a shining light, secret I must unfold. Variational laws encoders, they hold the key, unlocking infinite art and music. Let your thoughts run free. Coding brushes on the canvas, tale never told. Variational art encoders will break the mold. With acoustic guitar and a beat from the drums, we'll create melodies that resonate. Our minds have just begun. Unleash your creativity, let your imagination soar. Variational art encoders, opening every door. Art and music intertwined, a symphony in the air. With acoustic guitar and drums, our souls are laid bare. Oh. Coding brushes on the canvas, a tale never told. Variational art encoders will break the mold. With acoustic guitar and a beat from the drums, we'll create melodies that resonate. Our minds have just begun.